Right, so what you're saying is the performance, like when I went through the spheres, like it's only running at 8 ms, like per frame. Is that a now there's a reverb echo? Uh wait, I know the problem. Hmm. Wait, now the no echo here, okay. Just shop that around. Alright. So I think it's when so if I'm just running the game like this, is that is that lagging the stream? Because it's not running that hard, right? But I could make it run about 8 milliseconds, and then it is like, is that bad? Like, okay, this is this is 4 milliseconds. Is this a problem? Okay, good. I don't know. Maybe it went. Maybe when it does the graphical glitch, it's running too slow. I don't know what's going on. Okay. Yeah, it's very weird. It was completely fine on my end. I don't know. The moment I tabbed out. Oh. Okay, when I go off screen, these buggers go up a lot. Right. What about now? Okay, we'll do another test. Okay, so when I tab out, what about when I go to the edge of the screen? What happens? Okay, you know when I go off the screen, does it lag then? So if I go now, is that lag? Ah, just when I tab out. You know what it could have been since? It could have been. Okay, let me disable something else we've got. So I've got the only thing that I've changed since then is because the tabbing's not doing anything with the GPU performance uh, markers that we're getting back. So the other thing that we added was the hiding the mouse. So let's see if this fixes it. Okay, so I'm gonna tab now. Is it buffering? That's still buffer? Or is it lagging? Really? Alright, so we hide the mouse cursor. We're already hiding it, it's trapping it inside the window. So let's try again. So I'm trapped inside the thing. Is that buffering? What do we think? All good. No buff. What is the problem then? Uh it might just be Twitch then, because I'm not seeing anything my end. Uh oh, it did dip there though. I do not understand what was happening. That was weird. Oh man, when I stopped my stream, did it restart the session? Damn it. So I've got to have two VODs now. Damn Twitch. Um, yeah. So I'm just gonna go get a drink quick. When we come back, we'll get the Froxel binning working and the BVH binning working. Then we'll make some more models. We'll have a bit of fun making more models other than the dumbbells, and we'll make like a floor. Everyone needs a good floor, and we'll do some others obviously. Right, BRB. Right, welcome back everybody. So, where's we at? So we've got the models, multiple model instances now, which is great. Look at them go. So this is for the screen space tile binning acceleration structure. We need to do the Froxel based binning acceleration structure now. So I just want to quickly do that one. Just get rid of the printing code from the GPU. Store. Okay. So, sorry, CPU side. We need to enable our lovely. So this is the tile binning route. Let's disable that one. Let's enable the Froxel binning. So because of that, we've got to fix some errors. No biggie. Right, this has got to do the dispatch indirect side of things. Bum 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 bum. Pretty simple. Say for it to look in the globals buffer, indirect for the number of things it needs to dispatch by. We're going to indirect all the things, I'm sure about it, as we go. Alright. So it's a similar sort of method, right? We have one shader which calculates how many spheres get binned into a Froxel cell. Froxel being frustum space voxels, so Froxels. We just bin them into these boys. Just do a count. So we just do a pass over all the spheres and just count. Then we allocate using this guy. Then we basically use the same shader again as this one, but we actually bin them this time. Yeah, I want to improve that method, but for now that's just the way it works. I was thinking maybe we could yeah, heavily simplify this shader in the future, where it just bins them. Anyway. Yeah, until we do a lot of things, it's not really worth optimizing it. We kind of just want to add features first. Right. Right, then we just do the Froxel ray tracer. I think it's all pretty good. Okay. So hopefully this should work. It does have that glitch. Anyway, if the stream dies, I'll be right back. You know the drill. Alright, we're still here. So this is the Froxel one. Right, as you can tell here, they're running. So we're getting some graphical glitches. It's the way they're binning into the Froxel cells. Yeah, I think it's not binning into multiple Froxel cells properly, something like this. But it works good enough. Right, now it's time for the more complicated one. And that is, the lag is back when I tab out. Ah. Let's try that again. Did it lag there? Is it lagging now? See, it's not done it in the past, which is the weird thing. I'm not sure what's happening. Bloody weird. But it was when I tapped out, right, math room? When you experienced it that time. It was when it was tapped out, right? I was just trying to find if there's any pattern to it. Okay. So we disable this Froxel one, let's re-enable the BVH1 now. Now the BVH1, we build a BVH every frame for now. So we should do... So what should really happen? So we're kind of uploading our model instances every frame and our models every frame. What should really happen is we should, when we start up the application, or at some point we upload our models and then we fire off a constructor BVH for this model. And yeah, constructor BVH for this model. Oh my days, I just realized. We've got to do a whole sort of top level acceleration structure as well. Now, this is actually more of a complicated job. But we kind of need to do it before we can move on and do all the others, I reckon. Is that right? Yeah, we could do it. We've got time. We can do it. So, right, what do we need to do? So each model needs a BVH. We're not going to do dynamic ones, right? If you have an instance which has animation, you probably want it to have its own BVH. Yeah. So okay, we can jam this out. So basically, when we set these guys up, like a model at this point in time. Yeah, so a model's going to know the BVH, BVH nodes count, and you can get the number of leaf nodes from that as well. Just times 2, take 1. So each model is going to have its own BVH. So the BVH should be in local space of the object. And yeah. Something like this, I reckon. No, weird. So when we make our model, we shall also create all of the BVH nodes in local space. We'll calculate the bounds as well, every frame for each model. For now. In the future, we're going to have to change this, but it will be good. And then for each instance, we need another BVH. We need a top level BVH. Okay, I need to describe this a bit better with drawings. So the way the system works, right? I've probably made one in the past. Where's our boy? Here we go. Essentially, a BVH is a binary tree. If you have 7, well, technically it's different now. We have a variable number of balls per leaf node, but essentially if you have 5 balls, there might be groups like this in the tree, right? You've got 2 on 3, 2 on 4, and 1 ball on sphere 2. So each leaf node can have 1 to 8 spheres. So each model is going to have a tree like this. So when we ray trace, we can traverse through this BVH, which basically just has a bunch of bounding boxes. So yeah, then it'll make a bounding box like that essentially, but obviously in the space of the actual thing in the local space of the object, not in this sort of tree. But as an example, it's just bounding boxes all the way up. So these have a bounding box, these have a bounding box, then this one, right, node will store the bounding box around these two guys, right? And then this 0 will store a bounding box around this other ball from 2 and all of these guys. So that's all that happens. It's a tree of binary. It's a binary tree of access line bounding boxes. Bear in mind those are access allowed in local space of the model. So the problem is now we've got model instances, right? And their trees are going to be different sizes as well. Something that we've done as part of this BVH is we've made it a binary heap, which means it's a balanced tree. Right, so if we add another one here, it's got to go here. And why is this great? Add another one there, add another one there, do that, right? Why is this a good thing? Well, the best thing about it is it's very simple to traverse the tree. If I want to get the parent of 4, I think it's just divide by 2 plus 1. Oh, sorry, it's a very simple, we can just find it. It's this, right? You're going to get the parent, take 1, divide by 2. If you're going to get the left child, it's times 2 plus 1. Right child times 2 plus 2. Get the sibling, it's this, right? You get the depth of the tree with this. So it's pretty great. So we don't have to store 2 indices per node. It's all implicit. But it does have its problems. You can't make an unbalanced tree and have a more optimized path. But I think that's fine. So what is the... so when you have instances of this BVH to traverse, like you could copy and paste this this model BVH and put the other one directly next to it in a sense, and then make another tree, right, which just links the two together, and then that's a balanced tree, right? That's fine. Oh no, it's not a balanced tree because this doesn't have its children here, right? This one doesn't have its children here. This wouldn't be a balanced tree, therefore the binary heap wouldn't work. Furthermore, if there are 2 different models, instances of 2 different models, it wouldn't be a balanced tree either. So how do we solve this problem? Well, you have another BVH, which will have, so this is known as the top level acceleration structure, as they call it, whereas this is known as the bottom level acceleration structure, right? So this is bottom level, this is top level. So we'll do this as a binary heap, right? We'll do this one as a binary heap, but these are simply just links to a bottom level, right? Probably with some form of transform on it or something. I don't know. We'll see what happens when we get there. But yeah, this just links to a bottom level BVH. And this way, this one could be some balanced binary heap. And this one can also be a balanced binary heap, but all the different instances of the models, also all the different models can have different BVHs essentially, right? Different complexity in that. So yeah, it's going to be a bit of fun. It's going to be a bit of fun. So let's start off with the bottom level acceleration structures. So when we make those models, create all models, excellent. Leaf node spheres count. All right, let me just figure out what the hell are we actually doing. So we first run this BVH calculate bounds. So BVH reset or reset all of the... Okay, So for each model, we're going to run this. So let's quickly do that. So for, yeah, okay, let's just do the for. Okay, so model index 0, model count. Right, again. So we'll improve this as we add more features. So reset. Yeah, I guess we'll just read the number of, so we'll be like models index dot pvh count. Need to launch that as well though. So spheres. So these are the spheres of a model. So these are the model instance spheres. These will just be the model spheres. Bear in mind, yeah. Yeah, so I think actually, like the way we're launching these shaders and that, these shaders actually might stay in a very similar way, but we might have like a certain number that we can only upload per, sorry, that we can only update per build from scratch per frame, because it'll just be bad for performance maybe. Yeah, and it might be, the problem is it'll be controlled from the CPU. So maybe the GPU, I don't know, we'll figure it out. Yeah. So, what's the number of spheres? Well, we could actually just get this information from the model, but then it'll limit this shader to a model. When really you might want to do it for an animated model instance and it gets its own one. That's interesting. What would you do in that instance? Well, we don't need to care about it right now. There's that reality to the problem. BVH nodes count. We can calculate that based on the number of spheres, and then the number of spheres comes from the models. Like, by the end of this shader, do we need anything to be stored out? I think we're allocating it from the CPU side. Anyway. Yeah, I think we could just do this for now. I reckon it can work this way. Right, we'll store that in there as well on our relief nodes. We can do that. Let's get rid of that. Okay, so let's go for that. So leaf node spheres count. For now, we have a variable number of spheres per leaf node. Yeah, it's probably the way it's going to work anyway. So we kind of need to know where these. We need to know. Yeah, leaf node start index and leaf nodes count. Okay. So we kind of need to get those allocated. Right, so for the dumbbell, BVH leaf nodes count, start off as 0. So we also need the number of BVH. No, we can calculate that, I think. Whereas how did we work out that number before? Oh. So it is something you need to increment. Okay, so the start index of this is equal to whatever the count is. Then we'll do the thing again at the end, where we do the whole count, take away models, model dumbbell dot start index. So the number of nodes is times 2 plus 1, isn't it? Is that the way it works? Yeah, times 2 plus 1. Fantastic. So we'll do that as well. That should be the count, mind you, and then this one should be the number of nodes in total. Cool. So now we need to put in the code which actually calculates the sphere leaf nodes. Right, let's bring this in here. I've just realized this should probably be shared in some way if we make a bunch of models, but I don't know. For now, we just need to get one working, isn't it? So this one goes over all the spheres, and it figures out if they're in like a 2x2x2 together. So essentially, we get so 2x2x2, which is 8 at most, right? So let's just imagine it as a 2x2. If there's spheres next to each other like this in space, they get put together in a leaf node, right? If there's two together like this in a space, these two will be in a leaf node together, and obviously there's three like that. Those will be in a leaf node together as well. So that's all this code is doing. It's using it's sorting via a Morton Z curve, and it's using that to do it. Basically, so we sort them in Z curve order, which means spheres will show up in a linear array next to each other, which are positioned in a sort of a Z in space. That. Then the next Z. So 0, 1, 2, 3, 4, 5, 6, 7. They'll be positioned like that. And if one doesn't exist, there'll be a gap in the Z curve. And we sort of account for that gap and group things every multiple of 8, basically. So model sphere start index, isn't it? Yeah. So I want to go model spheres. Just drop it in there like that. Bam. Spheres count. It's not all those spheres, is it? Oh, take away this one here. Okay, so we're going over constructing that. It's just storing it into that temporary array. Not good. We should rename this to total now. This way it's easier. So I'll reset these every time. Those will just be set to total. Total. Okay, so now we're gonna get less buggy code then. Some model. Yep. We're putting this temporary array with the Morton index in the higher bits, so it gets sorted by the Morton index. Sphere in the low bits, 64-bit integer. Temporary spheres array where it gets thrown into. Then sort them using the sort it mate function. So equal -1 +1, fair play to you. So we're going to initialize model. Needs to be I think I just need this as a function or something. That we then just have a bunch of SDF stuff. Because I feel like this is just completely reusable for now. Right, model. Although we put in a function, all this persistent state. Yeah, so all this stuff that needs to be passed in a bit of a bugger. We might just copy paste it for the few times that we need it, I guess. Okay. So this will just be equal to model spheres count. This will be equal to model. Then we need to make sure that we update. Okay. Now we just need to update the total. Spheres count to model spheres count. And then just update the total BVH. Right. So I feel like, all right, here's what we could do. Make this a for loop, right? And then just do an if statement here every time. Then just go if one. Yeah, this is the best way. Because basically functions suck. So there's another for loop. And we'll literally just do model index, right? And then we'll literally just do 0, model count, right? And then we'll just do a switch statement. And then Bob's your uncle. Something like that. Gonna be good. Gonna be good. So every model dumbbell is just now model index, and then voila. Scales. So here is where we'll do a magical switch statement, and we'll just go model index, and then we'll literally just do a. We need to leave a D hanging out, and then what? Case 0. Oh, not 0, right? Model dumbbell, of course. And then we'll do a default just in case. Just on a mess anything up here, we'll do a little abort. All right. Dun, 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 dun. So when we add more types of models, we'll just put them in here. Done. So next thing to do is so this means now we should have the leaf node counts set up for each model in here. Yeah, I think that's right. Leaf node counts, BVH nodes count. We store out into this leaf node spheres counts, so each count for each leaf node, how many spheres that sit there. We put that in there. No. This needs to be the total, isn't it? Just append it on the end and away we go. See, it starts off at -1. Then it's going to land on 0. Has this always been... Something's a bit wrong with this. Yeah, so the end this needs to be up by 1. Why was that assigning itself? That's not good. Yeah, so this number, when we leave the for loop, needs to be upped by 1. Because it starts off at -1. Then we also need to make sure that when we insert it into this array, it needs to be offset by models model index dot leaf node start index. Again, just demo code, so it could be a bit silly. That's fine. So it's fine. Store the spheres in the array properly. What else? Right. So now each model knows knows where its leaf node counts are, how many leaf nodes it has. We need to allocate the number of leaf nodes though. We can do that. Oh no, we've already done that. Yeah, we've done that. That's good. Okay, we're nearly there with the bottom level BVH. So now we need to go to the BVH reset. So we go over all of the models and we set their nodes, and we launch a shader to do that. So we have to know the start index. So we should pass in a start index as well. That comes from here. Hopefully we can make this more... Actually, it might not need to be GPU driven in the end. Yeah, we need to have that in the... Okay, in the shader. Cool, so if the index is more than the count, great, and then you just do a lovely BVH nodes start index plus. Okay, so we're just going to clear it to infinity. For the min and max, it's not a bug. We just need to clear it to something that's, yeah, just something consistent. So we just chose infinity. Okay, so jobs are good in there. The next one is the calculate bounds. So this one is the thing that constructs the BVH. 4 is the bottom level BVH for the model, right? So again, I think we need another one of these. So we'll go ahead and do that. So let's have a look into this. Is there anything else that we need while we're here? So you got the model spheres. So the spheres for the model. Right, you need to know. You also need to know the sphere start index. Okay, I think that'll be alright. You need to also know how are you going to index this guy. So you need a leaf. Leaf nodes start index. That comes from the BVH. Leaf nodes start index. So I guess I'll do a quick take on how this shader works. Right. Good. So how does the shader work? Well, it's basically, I don't know if I have the article anymore. Right, it doesn't matter, I don't think. So essentially, right, we simply we start off, we launch a thread for every leaf node. So thread. And each of these it knows how many spheres it has, right? So this one might have 3 spheres, this one might have 7 spheres, this one might have 2 spheres, and so on. And they're in order. So it can know like, these are 3 spheres that sit next to each other in memory, then after that the 7 appear, then after that the 2 appear, right? So essentially what we do is we calculate the bounding box around those 3 spheres, calculate the bounding box around those 7 spheres, right? Every thread goes up to here, and then basically says, it goes up to its parent, and then, hey there, thank you telephone, how's it going? What we're doing, we're adding support for multiple instances of some 3 models, basically. Currently trying to fix the BVH renderer. But yes, basically what's going on. So we go up to the parent node. Each one of them goes up to the parent node. They set their... What do they do? Yeah, they set a marker to say, hey, I've been here. And then it terminates. The first one of the children, because there's only 2 children, goes up, sets the marker, and goes, I've been here, by the way. And then it'll exit. The second one comes up, and it's like, oh, something's been here. So what I'm going to do is I'm going to get my siblings' bounding box, this guy, and I'm going to get my bounding box, and then I'm going to create a bounding box around those guys. And now I'm going to go up to my parent, set the marker. Oh, I'm the first one who's here. I'll terminate. Meanwhile, these guys have been doing the same thing, and this one will come up and then, get this one and create the bounding box around all those guys, right? The bounding boxes. So this recurses up the tree and does all that in a parallel way. I want to see how much this scales. I'm gonna have to probably. There's another thing is where I can optimize it a bit, but for now this will do. So I've got to fix this. So we've added those new things, right? What was it? We've got start indices for the BVH nodes and leaf nodes. Whenever we index these buffers, right? Basically, we've just got to adjust those. So away we go. So this one is now BC leaf node plus that. Boom. Bob's your uncle. Then the spheres. Where do we index? Is this the only place we index the spheres? I think it is. So this would be BC spheres start index, right? So this is where we calculate the initial bounds around the spheres. And then the final one is the nodes. So this is where we do the lovely... Yeah, this is where we do the lovely traverse up the parent and, set the flag to say I've been here. If, terminate that thread. If it's the first one here, if it's the second time it's been around, grab the sibling, calculate the new bounds, and store it. So we've got to do a something like this, right? Oh, this is so annoying. ABS. How to do that? Right. So it's got to do that for the sibling one as well. Okay, so that's all adjusted, which is super great. The next thing is, so this constructs a bottom level BVH just fine now. So we've got our bottom level, so all of our BVHs for our models are going to get create every frame just fine. Now we've got a problem that the ray tracer, okay, it's only going, it's only been programmed to go down a single acceleration, a single BVH. So what we might do is let's just give it to make sure everything's working fine. I'm thinking, why don't we hard code it for just the one instance for now, and then add the top level BVH just to make sure that the bottom level one works, right? Okay. So what do we need? We got spheres array. We need a spheres count, isn't it, as well? But those spheres count can actually go. It's not a good idea to keep that around. Model instance spheres. Total number of BVH nodes. What do we do with this one? Where's that? Yeah, we might be able to just use model 0 dot for now, right? Bad idea long term, but for now. Okay, so you've got the spheres, and it should just pick up the first node in there, in those BVH nodes, and just do. Yeah, but it's not even going to get a model. Yeah, okay, we'll hard code it in the shader. That's fine, that's fine, that's fine, that's fine. Okay, so we need the model instances in there then. So I can get the transforms, right? We're going to pretend. Right, I got it. So we need the model instances and probably the models as well. Maybe. Maybe not. Alrighty, so BVH. Okay, so we'll just pick out the first instance and we'll have to transform into the local space of the object, of the model, right? Okay, so let's describe what's going on. So this is the problem, right? You got yourself a view frustum. Let's find a bit of empty space. Let's just go up. Screw it. Got yourself a view frustum. Bum 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 bum. There's the near plane. Now, up until now, the models have just been axis aligned with the view because we've not had model instances and anything like this. But now our axis line bounding boxes are going to be axis aligned in local space and not necessarily world space or view space. So when we have a ray that shoots out into the scene and hits a model instance, it will traverse down. So, okay, maybe I should draw something else quickly. Debugger. Imagine this is a BVH, right? Something like this. So this would be our top level BVH, right? This is the root node, this outer one here. These two are the left and right children, right? You shoot a ray, you hit this bounding box here ultimately, right? And it's a leaf node, so we know it is a and then it has some information in that node to say, oh, it's for this BVH. So, sorry, it's for this bottom level BVH for this model, right? So now we need to go. This is code we've got to write some after this simple code, but then but we're going to skip that code for now. And we're just going to get this part working, right? And then we will get the transform of this bottom level of this model instance, and then transform this ray into the local space of the object. So then that would mean that the object is axis aligned, but the ray is in object space. So it's going to come across like this, right? So the ray is going to come across from the side, as if we've just rotated the whole world. So this becomes axis aligned again. That way we're working with axis line bounding boxes again, for this BVH. So this will be another BVH, which is then filled with spheres. And voila. This is what we're going to be getting working. So, we're going to start off with a model instance for now. So it'll just be like model instance equals BC model instances 0, right? So we need to transform that ray. So it's in view space. So it needs to go into world space and then into local space. So what do I want to achieve? So I think we'll keep them. So why are they in views? Oh yeah, good. Right. So these be world space. Let's be careful there. So these need to be in local space. That's the BVH viewer. We'll get to that in a bit. One at a time. Now we need the inverse direction. So that'd be some more world spaces. What else? Wait. Local space. What am I doing? Okay. So we need your model. We need the ray origin as well. Whoops. That's in world space. Ray origin, local space. Okay, so now we just need to create those 3 variables transformed. So, yeah. So we just need to say ray origin, local space, so we got that right, equals multiply position, transform 3D, model instance, dot, so this is actually going to be world from local, and we actually want the inverse of that. So we'll just do inverse, transform 3D. Okay, so we need to do that same thing again for ray direction, and then ray inverse direction. Oh, sorry, inverse ray direction. It's more of an optimization that. So that'll be, these are vectors, so they're v, so no translation wide. And you need to translate the ray origin world space, ray direction world space, inverse ray direction world space. Okay, so that should basically get the shader working, but only for for the first instance, right? So let's take that for a spin, then we'll fix the BVH viewer, and then we'll add a top level BVH. Why no work? Or as this spheres count to cap it. I think I've got a nice global for that now. Rightio. Super good. So, if the stream dies, you know the drill. I'll be right back because AMD crashes if we do anything dodgy, but it should be fine. We've got a lot of safety code in the BVH stuff, in the BVH ray tracer. So here we go. Right, it's running. We see things moving, although it doesn't seem to be correct in any way. So if we disable the rotation, then we can start. All right. Interesting. So we kind of see something. All right, I feel like something's up with the transform. What have we done wrong? So we're going from so we're in world space, going from view space to world space. Then we're going to local space. You know, let's make this a little bit more readable. Yeah, so we're just, you know, we're going from world to local, so that just all works right there. That shouldn't be any, that's not the problem, right? So it could be something to do with how we're, like, we might be assuming we're in view space still, or world space still, whatever, right? We got some of this sort of like near clip plane distance stuff, pixel size at near clip plane. Yeah, T min, T max. Right. Closest hit depth. That's another interesting one we're gonna have to deal with when we do multiple model instances. Yeah, that's definitely interesting. Right, it could be the BVH. Assume that the BVH. Right, we don't know this. So what we should really do is put a breakpoint in and just analyze some of this stuff, right? What is it? All of this, right? So we should really chuck a core breakpoint in there. Boot up the GF. And what she says is, oh, you son of a. Models, oh sorry, P models. Is that, no, okay, it was still the same problem. Models, model index. Give me the answer. Okay, so your start index is 0, perfect. Number of leaf nodes. Number of nodes. I think that sounds about right. It feels very right because we've got 207 spheres. Did we populate them inside the buffer correctly? Hopefully. Crap, what is going on? Why can't I move this thing? Oh, crap. Man, it spiked there. It could be because we're uploading a lot to the GPU now. That could be the bottleneck, is the transfer rate. And we're not profiling it. Yeah, I think we're transferring too much to the GPU. Let's make some of these numbers less. I think we're transferring way too much. Let's just do 128 instances for now. Let's do, I don't know, 32 models. Let's do, we'll keep the number of spheres quite high. But how many spheres buffers have we got? We just got probably tons of these guys, right? Because what are we uploading to the GPU exactly? Doubled that now. Yeah, I think this could be where the problem is. We're just uploading too much of this. Let's reduce this number. Let's half it, right? Let's half that number. Damn it. Right, let's just stick with 80,000 as a capacity for now. We'll, if we need more, we'll just make it GPU. Oh no, why don't we half it again? Yeah, if we need more, we'll just make it GPU driven, I think. And not upload that much data every frame. Yes, this is cap is like 40k. 40,000, right? Proper 1,000, not computer 1,000. Okay, I think that will help with the lag spike that was getting. Seems to make the most sense. Right, so why are we getting some problems here with the with the BVH sort of traversal? Do we know if it's the traversal? Well, we could debug print out the bounds. And if we debug print out the bounds, why don't we just view it in RenderDoc? Right, the information. Right, so plop into RenderDoc. Make sure it still runs first. Alright, running. We're uploading less data now, so we shouldn't see any lag spikes anymore. That's the hope. Okay, so we're going to RenderDoc. So with RenderDoc, we can get some lovely information. We can literally see the buffers and stuff like that. I just need to figure out which one it is. I don't have any good names. You know, should we improve this? Like, we don't have names here. Right. So there's a lovely extension where you can basically just do an object name or something like that. I need to add the extension for it. Vulkan. No, I don't even remember it. We'll look for the header file. It's not debug report. Man, I really know a drink, man. Damn it. It's not debug. Or is it debug marker? Set object name. This is it. No, this is AMD's all. Right, let's look into this extension. Deprecated. Yeah, debug utils. Yep. So debug utils is the one we need. And this allows us to set an object name. So it'll be pretty easy to do this. And then we'll be able to easily use render doc. Right, I'm just gonna get another drink and then we'll carry on. BRB. Right, welcome back. Oh my days, it's just got a bit chilly in the house. Back on that hoodie. Ooh. Okay. So we're quickly gonna add this debug utils thing in so we can set an object name. So we get lovely buffer names here in the right hand side of render doc and stuff like that. So it's just easier to know which buffer it is rather than remembering, oh, it's number 205, and then you add more buffers and then it just, yeah. Oh. So, set debug utils object name. That's our boy. So this is an optional function pointer that we need. So we have our lovely X macro interface to sort of load these function pointers for us, so there's less overhead in the driver. Well, not in the driver, but in the loader. In the yeah, but and these are stored in a global data structure around about here. So we need to have our optional Vulkan function pointers. So we'll manually code these in. So it's pfn, that's the function pointer type. Like, that's just the way it works, right? If you go into the header, like for every function, there's a pfn underscore, and it's all type deft exactly where you need it. Just super great. Perfect. So let's go full ham and load this boy up. So where we do those loading, create device. Interesting. We've already got one of these here. Oh, that's funny. Debug utils, interesting. We've already got it in as an extension. Excellent. So, right, it's an instance extension. Okay. GPU, Vulkan. What is it? This one. So we just load the function pointer. Good old function pointers. Right, let me use cast into pfn of that. Alright, we're loaded. So, now every time we create a buffer, buffer in it. Yeah, this boy. So, here's the wonderful thing about this. We've already got all the names in there. They're just stored in here as debug name. So, it's going to be great. If this function pointer exists, right, therefore the extension is loaded, we can now call into this guy. We pass in the device. No scale these boys. Fill one in. Just duplicate that because I'll probably forget it. Right, so info equal this. Okay, so structure type, So that's obviously just structure type. Then it's just whatever this is here. Because they allow you to like chain them all together, daisy chain structures together for extensions. It's alright. Null because we're not extending anything. If there's an extension to this data structure, they'll typically daisy chain another structure like this with a structure type on as the first field. So I can tell what it is. So object type is object type buffer. Then the handle is whatever we got. So that's whenever we created the buffer somewhere. But anyway, it's this one here, right? Then the name itself, resource debug name. And that is literally all we need to do. I think it gets back a result. From what I remember seeing. So we need to do a gpvk set. So we'll assert there if we have any issues. Cool. So that's for buffers. We want to do it for textures too, luckily. Very simple. Boom. Image. There's images and image views. Let's just do the image view. Crap. Well, let's just do the image. Screw it. Yeah. So with that addition, we should have lovely debugging information in RenderDocs. So if we just, or debug names for the resources. I'm so bad at maths. I struggle with high school maths. That's alright, no worries. I kind of am a bit, 50-50 with that as well. It's not my wheelhouse, maths, but when I need it, I'll learn it. So yeah, we've got a bit of a problem. The names kind of suck. The names just literally have the name of the thing. Something's just called globals, right? It doesn't tell us what it is. So let's fix that. We've got debug name max size or something. I think we do. So we'll just do like 256. That's like plenty. Buff, size of buff. So why are you programming in Rust LSPL? Have you just sort of ran a load of code in it and now you've sort of developed a different feeling for it? Right. So we'll just do like, so for this one it's an image. So we'll do image. We could just do texture, but I don't know. Image, and then put the name in there. Right, because unfortunately RenderDoc doesn't do this. Even though it could have. Pretty sure. But maybe there's a reason why it wasn't a good idea to do that I don't quite know about. Right. So yeah, we're just going to take this around now and fix up the buffer one, and then we should Everything we need. So you give that a run, still works, fantastic. Launch it up in Renodoc, got some lovely names now. Yeah. Now we can debug what the hell is going on. Why they got dot dot dot? Okay, that's just because Renodoc thinks it's too long. That's fine. Come on, the way it just goes, does dot 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 on the notes. What is your problem? No, I found the way it cuts it off there. Maybe it's a bug in the current version I've got. That's alright though, it's way better than it was. So what was it looking for? It's the BVH. We're looking for the BVH nodes, right? This one. So we view the contents. We've got a lovely format here. Ta-da! So this is in local space of the object. How many nodes is there again? There was only like 40 something, wasn't it? Got the number. We printed them out in the right, where is it? Where it does them? Right, there's one where it clears them all. Yes, this should set them all to infinity, but it's not all infinity for some reason. This should be BVH reset. Want to use code generation optimization, crane lift. Oh, okay. Yeah, Rust is a bit of a pain for trees. Yeah, and you use a lot of trees in a compiler, didn't you? Oh, a bit chilly. So I think this is it where it does the reset. Yeah, BVH reset, this is our boy. So, why did that look weird? Right, I'm glad we did that today, it was pretty cool. So BVH reset is just going off the number of nodes. Right. Seems pretty good to me. Then it's just storing in there. Then this one launches after. So it's, you know, synchronized. It's all fine. Um, yeah, something's wrong. I think something's wrong with this viewer, like this information we're getting back. How can these go like this? That doesn't feel right on this after you reset. Something's fishy. Anyway, what does it clear this up to? This one, 110. Why does it clear that much? It's the number of leaf or number of nodes that you have in total. Right, it's fine. It's like 110. Yeah, so ignore all the other ones. So effectively, if you see an NAN in here, then there's a bug. Right, there's no NAN that I can see. All of these zeros feel, all of them that go diagonal like that feel like a bug happened in RenderDoc, not the data in the GPU. Well, maybe I could be right. With a stride that's larger than the size of each row. Oh, have I added anything to the BVH node that's different to this data structure? I added this N. What is that doing there? Right. Alright, scare it. Right on there was supposed to go, thank you. Why do we got this again? Oh, for the number of spheres, damn it. We need it. Ah, oh, bugger. Um... Oh, failed to pause. You bugger. Right. Even. How do you update this definition? I don't get it. I just have to click it once. Click. Then click save. Cool. Delete the other one. Right. Jobs are good. So that's fine. So we clear them all out now. So we're looking for like an So we get to about here at 94. Right. So when we go here, 94. If we have like an NaN or anything, or an infinity here, then there's a bug. But it seems pretty legit. So now we can actually look at the sizes in that. Like, the root node. Yeah, this seems fine. But the max is bigger than the min. And this split, these are the two left children for the first. This is the root node, left, right of the root node. And they seem to be fine. They seem to be dividing, basically, across the x-axis. Although that n number's not being updated. Something looks wrong with n. N is just number of spheres for some reason. Oh. Okay, we found the problem. This is the bug. This is using a node index. Sure. ABS equals BC BVH node start index plus see if there's any more of these. I don't know if this is the problem though, because I swear it was just going to be on 0 anyway. Let's just double check all the array indexes inside here. That's offset. That's offset. They're all offset in there. That one's offset as well. They're all offset. Looking good. Feels like it's the problem, but right. Still got the bug. It's still not rendering right properly. So let's just check the data one more time. It should be fine. Right, it's coming from this guy. Interesting. Um, right. One more check. There's the reset. BVH nodes. BVH node. There's cleared to infinity. Go to the next one. Okay, the n is still not set, which leads me to believe that this data that we're reading the number of spheres from is completely wrong, and that's a big number, and it really went over all those. I would have minned it. Excellent. Okay, so how is it setting that? The counts. Right, so where the counts have been worked out. Um, So this is when we make the models and initialize the number of spheres inside of a leaf node. Yeah, so you start them off there, that's fine. Based on the current total. Um, so it's the start index plus the offset. Initialize it to that seems fine. And then just increment it by one every time. Wait a minute. Why is it shift F4? Why is it doing that? Right, get diff time. I am confused. So we used to do it, we still used to do it right here. That's storing the number of spheres. And this should be like 1 to 7 at most. So 1 to 8 at most. I'm not sure how this used to work. Like, it shouldn't have worked. We get out the number of spheres. We don't do anything with it. Oh my days. Okay. There's 2 bits of information in there. So I threw this thing in to get it working, and obviously it's confusing. So we're storing in the higher bits the start index. Yeah, that's what we're doing. Damn it. Okay, so store those in the high bits. So it is going to be a bit of an odd number, right? That's the way it is. We've seen a couple of zeros in there though. Oh yeah, we're going to get zeros in these because these are not leaf nodes, right? And they'll be uninitialized memory. Yeah, that makes sense. Okay, we're doing good. We're doing good. We're doing good. So I think this is all fine now. The issue, well, the issue must be from okay, so this should have been an issue that we've obviously fixed. It's just the way we're traversing it down the tree then. This must be it. So let's go to the BVH traversal code in the ray tracer. What are we passing in again? So we're just assuming that you're starting off from like, so the first model is going to stick. Yeah, we're just assuming it's the first model's BVH. Yeah. Ah, we're not offsetting the spheres. Yes, we're not. We're reading the wrong spheres, I think. Something like that. So here. Okay. So sphere index. We need to offset it based on model instance dot spheres star index. Is that right though? So you get the base sphere index in that n variable, damn it. And n, when we uploaded it to the, oh, where was it? In here, the index is relative from the model. Wait, from the model. What? Yeah, from the model, but not the model instance, but it's a copy. We just copied them all over for now. Right, okay. This is going to be a problem when we do anything different. Because we're currently copying the spheres from the model for every instance. It's not really that great of an idea, but it's just the temporary code we got for now. To do this will not work when we have model clusters. Cool. So I think that's actually. Plus this thing for us. Right, that should work. If it crashes, you know, I'll be right back, but it should be fine. No. Right. So when we hit a leaf node, I know it does feel like it's something to do with the traversal though in a way. Just the way it feels like it's something to do with the boxes, right? Hmm. Oh, are the spheres in world space? The spheres got translated into world space. What it is. So what's possible? Oh, bit fields. Nice. I wonder how that would work though, because they're kind of different on every platform. Like I've got them in my compiler HCC. They follow whatever the host is. So on it's a bit different on Windows and but we got them working. I wonder what it'll be like. Find the hash map. Oh, that sounds slow. Pointers, eh? Amazing. Someday we'll get them properly. I could technically add pointer support, but it would just be limited to certain hardware. Yes, the problem is the sphere is in a different space, right? The spheres that we get out, because when we did that sort of clone thing, emit, or emit them, we actually translate it from what into world space from local space, which is just a temporary thing to get the others working. So we actually need to translate it back, right? Get your sphere out, and this will be from local from world. Oh yeah. Would you look at that? See, the other one, the screen space tiles, actually, these are not missing from the back. So there's a bit of a bug there on that one. Right, so let's get the BVH viewer working again. And then we can think about the top level acceleration structure. I might save that for another day, but let's just get the other one working. It does with the outline, doesn't it? Definitely. Yeah, I don't know. Yeah, I don't want to keep it, to be honest. Just a graphical glitch. But yeah, it does make it look sort of like Borderlands in a way. So let's enable the BVH viewer. Right. This one. So, right, broken a bit of code, no worries. Get rid of that. Right. All right. So in the shader code, it's definitely wrong. So in the viewer, we need to do a similar thing to all this is doing here. We want to get world space. Oh, we'll just take all this here, right? So paste that in there. So the raise in world it starts with a view space, we move into world space. Then we make local space versions when we from this model instance that we've hit. We should actually test the rotation out. I didn't test that out. Obviously it works because I've moved the camera around, right? But still. So we've now just got to be using. We've now just got to fix up anything like ray origin to be ray origin level space. And then obviously the ray direction side of things as well. Inverse ray direction, that's here. So we're just testing against a bounding box, and there's nothing else that goes on. It does kind of use some sort of size in pixel space, so that could be incredibly wrong. We'll see how that goes. I need the model instances in there as well. Oh, did we not guard against that? Yeah, model instances buffer, we didn't read only against that. Not good. Didn't put sync code on it. That could have been a bugger. But yeah, so just got the model instances buffer there. Plop that in there, and away we go. So this shader is more likely to crash because I've not got some bounce clamping. But yeah, hopefully it doesn't crash. Okay, so you see the BVH? I think it's fine. It just gets bigger than a pixel when you get further away. That's fine. Here's the lovely viewer. Yeah, we haven't got any sort of it kind of just draws through the spheres at the moment. But maybe that's what we want. Nice. Alright, how's that? Is that lagging the stream? That's fine. Okay. Kind of forgetting what I wanted to do next. What was the thing? So I've tested the... Was it with the BVH viewer? There's something that I wanted to do a little thing. Was it something to do with the BVH traversal code? I'm not sure, to be fair. Right, so next thing to do is actually to build another whole BVH, but it'll be a bit easier, but it'll be working off of model instances instead. So I have to go over all the model instances and basically compute a new BVH every frame as well. So the code will basically be like this. So we should probably copy paste this and call it top level. Make a top level version of this. I don't think it's going to be too difficult. So I think let's just copy paste it. Let's call it top level. And so this is just going to go over all the model instances, and they are leaf, and then those are leaf nodes. That's a good point. Let's make a commit. I always forget to make commits. Yeah, because that way it would be... Ooh. Yeah. So this one is like something like add model instance support. Just missing the sort of top level BVH. Not bad. So for like a top level version of this, it's gonna be taking the model so it's gonna be, instead of spheres, it's gonna be an array of model instances, maybe? We used to have an array of model instances. You'll need their bounding box. Like, how do we get their bounding box? Like, so you got a transform. The bounding box should come from the model itself, transformed into world space, and then you sort of take another bounding box of that. So when you compute, yeah, but you have your BVH nodes, isn't it? Yeah, I think we have all the information we need. So the number of you kind of need to know where to write this information. How many nodes we're going to have, we can have that as well. Yeah, I think that's what we need. I think it's pretty easy to do this. So we'll do the whole same as the other one. Yeah, this is some magic to sort of get the spheres to line up properly. Do we want this? Yes, we want the same code. So we need to calculate the min and max of this. It says the two spheres. Right. Of the bottom level model BVH. So the way we're going to do this, so the leaf node index is going to be the model instance index. So we should be able to get the model instance. And that one would be model instances, leaf node index. So we get a thread per model instance. Now I want to get the model. Finally, I actually managed to output some x86 machine code. Nice, that's pretty quick. So that'll be model instance dot model index, something like that. So with this, we have access to the BVH, and on the root node, yeah, the root node will have the bounds. It will have the bounds. So, but it's the bounds in local space of the. Let's go back to our lovely diagram. So we've found. So remember, this is the BVH for the model, right? It's got its own children and then spheres inside those children. The array comes across here, right? This is the array. This is this thing. So we need to get the bounding box for this thing. Get each corner. Move into world space. Calculate the new min max, and that'll be this bounding box. And this would be the bounding box for this whole BVH, at the top level BVH. So it is simply just something like so model instance world from local, and then we need to fetch BC BVH nodes model.bvh nodes start index, okay, plus 0. We'll do the plus 0 because it symbolizes the root node, I guess. Yeah, then we're going to say dot min dot x. Then we're going to translate this boy, mol point, into world space. So we get these there's a min position and then there's a max position. So min world space, max world space, but this is obviously not min max now because you've transformed it, right? So how do you do that? Well, you need your sort of like what do we need to call it? P world space, P0, P1, min equals min of P0 wall space P1 wall space, and then max is the maximum. I think that's it, right? I've already got them up here. So thinking about that, yeah, it's been a week. That's not bad. Did a good job there, Elspeth. Um, um, so let's go over this again. So again, our leaf node index, which is our instance index. Fish out the instance, fish out the model. Get the root node. I should probably stick a comment. No. Yeah, get the min and max, transform those. Let's double check. So imagine this is min, this is max. Name right, is it? We need to get the corners. And then do, so we need P1, P2, P3. That's for 2D, but there's actually 8 corners, right? All right. Is there a way to cheat that? No, there's not. So before we do any of this, let's right, so let's do this. And we'll call this local space. So now we can go ahead and do something like so. F3 times 3 min local space dot x y and then z, and then we can just basically just switch between them all. Do we really need like if you're working with offsets, you only need half of them, isn't that correct? Yeah, if you're working with offsets, you only need half. We've done this before. Might be an easier way to do this. So if you have a half size and a position, you can translate the position separately and the half size separately. And then it's just a case of flipping all the dimensions, basically. Then it's just a case of flipping all the dimensions and adding, versus doing a whole bloody transform, right? Every time. It's probably better. Probably better for performance, I think. Maybe. You should be doing it like 9 times or whatever. Yeah, then you just do a for loop. We've done this before in the UI code. Where was it? It was the like somebody's like translating the ABB transform. There's a lot of things called half dims as well. Somewhere. How many for loops we got? Got many for loops? This is it. Um, right, so I still translated the half dimensions and then I went over all of those. Oh no. Um, okay, maybe it won't work. It should do. Because if you sort of rotate, that's not really a good idea of rotating, but say if you rotate it just a little bit. So you've got that one. If you flip it, yeah, we'll go there, isn't it? There was just, yeah, sorry, if you to get the perpendicular, it's not gonna be right. Unless it's square, I think. You could do opposite. So you might be able to get away with less transforms there. You could probably get like the min. Yeah, I think you did it as like a half size. You could probably do half of them and then flip it the other way. Um, that makes sense. Let's give it a go. So you do something like max take min. And you want your sort of like center position, which would be add we'll be adding min ls. Okay. So from here you would just get your sort of four sides. So call it V. So you'd do half size. Mol, I need a mol p for. So center position, walled space. That's a mol p, center position. I think you save on a few transforms. Not massive amounts. So you need four of them, you need half of them. Is that right? So given a cube, what do you need? A bit different, isn't it, than the 2D version? Given a cube of some kind, you need. So imagine this is like bottom left. Because if you have a half size going from the middle to the end, you can just flip that and get this one. You have another one which goes down to there, you can flip that and get this top one here. You have another one going down there, flip that, get this one up here. And flip that, get that on there. So yeah, you need 4. So you can just get the lower 4, and then you'll get the higher 4. Basically. Or do the higher 4 and get the... whatever way you want to think about it. So you could do something like that. Or, yeah. So... negative, negative, one of them negative, the other one negative, and both not negative. That'll do it. So you get those positions there. Now it's just a case of adding them to the center position and then taking the min and max of all those. Why did I get rid of the infinity thing? That was not a good idea. Need that. Okay, so effectively we're just going to be doing min equals the min between adding so given we've got this sort of rotated sort of box, you want to go to each of these guys and find what is their sort of max XYZ. So you only really do it for the, you just want to compute. You just need to compute the like the half size in world space. The biggest one of those. So where's the half size? Shoot. So you need to compute half size world space, and you just want to go over all of those and find the max. So it's then it's just add B0 world space. Center position. Oh no, we're not adding. Don't mind me. Half size world space. We might have to do negates, do it a second time around. Yeah, but then you might as well just do an absolute of it. I think you do an absolute space. So you have these positions. You do an absolute space. Then it's just 4 of those. And then the min and max is literally just take away. That is subtract center position, world space, half size, and then max is add. I think that's the best way to do it with the minimal amount of multipliers and adds. Just got to double check it. So I don't need this anymore actually. So get the model instance out, get the model, get the min max in local space, get the half size in local space. Now that's the full size. What's going on? I think the code I generated. Awesome. Nice stuff. You got this, else pill. Right. So half size in local space, center position in local space. Move that into world space. Calculate some positions on the bottom, on the top. So 4 positions at the top. Right. Is that enough? Yeah, because you can just mirror those and get the others. Yes, you've got 4 offsets going to the top corners. Do your half size, get the max of all those in absolute space. And then your min and max is just take away from center position and add from center position. Should be it. That's pretty cool if that'll work. So the next thing to do is just carry on the rest with the rest of the shader. So the rest of the shader just simply needs to do that whole thing we mentioned earlier, where it just goes up the tree and atomically sets things. I think the code just stays the same. So it just goes up the tree, sets a marker. If it wasn't the one that set the marker, then it's the second one that came by. Get the sibling node, and then calculate the new min max given your sibling and yourself, and go up the parent again. Yeah, that's all good. Oh, I forgot to link it. No. So that should be the top level BVH code to generate it. We've now, there's a couple things we've still got to do. I need some models. What have we still got to do? Yeah, so so now we've got the so still obviously got to plug this in CPU side, and then in the ray tracing shader we have to traverse down a 2 BVHs. We have to go down the top level, and then when we hit the bottom level, we have to then go down a different BVH within the same shader, which adds complexity. But yeah, it'll be right. But yeah. So there's a couple things I have to do. So I'm going to save that for Tuesday stream, where I'll be on at 6:30 p.m. GMT. So yeah, it's not bad today. Got some instances working. We just got to get the BVH stuff working again. But we're close. This is someone to raid. I found a code on music. That's for programming, I guess. Right. I'll see you all in a future stream. I'll see you on Tuesday, perhaps. But if not, have a great start to your week, everyone. And I'll see you in a future stream. Right. Catch you later. Bye-bye. Thank you for coming. Bye.